Okay, everybody. There is still a bunch of people missing, but we need to move on. If you could have no talking for a bit. You're going to split into two in this session, I think, in a way, in that, and I've said this already to the people who are here on time, that is, there was three videos to watch. One was half an hour, which I know would take longer than half an hour to watch with pausing. I'm sorry if it took way longer than half an hour. It wasn't meant to. But anyway, if you've watched that video and then you've watched the other two backup videos as well, which were much shorter, they were just like, by the way, kind of videos, and you understood them and you're ready to make a crack at the work itself, do it, because the more practice you get, the better. On the other hand, if you didn't watch the videos at all, then what I'm about to do here in the super summary will not be good enough at all. Don't ask me questions if you haven't watched the first video, because it's longer for a reason, right? I don't want this mini super summary lesson to be drawn out by people who haven't watched the video. If you have watched the video and you've got follow-up questions, of course, but please don't waste everyone's time if you haven't watched the video. Just start watching it now. Yeah? Yes? I won't wait for you though. This lesson here, and if you're watching it back later, this video here is just a super summary of the key formulas that were brought out of the video and another example to illustrate that. Now, this is for the people who just want to see one more example to be really confident with confidence intervals. If that's not you, you don't need to watch this video / follow on with me right now in class. You get stuck straight into it. The exercise work is in the learning schedule. Just do it, right? Practice is probably more important than watching me. If you are following on, it's because you just want that extra confidence for some reason. I don't mind what that reason is. Who is following on with me? Okay. Just you guys. Okay. So I'm assuming you've watched the video from this point onwards. They are the two key formulas that came out of it. One was the margin of error, which is Z multiplied by P hat multiplied by 1 minus P hat all over N. And the confidence interval is P hat minus M, P hat plus M. Now, in your information sheet, I mean, that's a really nice, simple way of writing it, I reckon. The information sheet looks like this, just so you know, it is there. They don't have brackets around the confidence interval. I don't know whether that's just a dodgy copy of my information sheet or whether they don't normally put brackets around it, but I reckon they should. But you can see that that margin of error M, that formula there is exactly the same as what's there and is exactly what's there. So it really looks complicated, but I reckon my way of writing it's a bit simpler. But, you know, whatever. So they're the two key formulas. Now, the question is, how do we apply those formulas to solve a problem effectively? And I'm going to do that in a second. But does anyone have any questions about what those formulas are or anything else? You know, thinking about your experience in watching the video, and did it raise a question about the formulas that you'd like to ask? I don't know why I'm talking to this side, but you'd like to ask now before I move on. No? So you can kind of see that effectively P hat becomes the center of a distribution. And this is like the scale factor from the standard normal distribution multiplied by this mean here, P hat times 1 minus P hat over N, which is very similar to this formula here. Sorry, I said mean, I meant standard deviation here. And we remember, I hope, that for a population of an unknown order, we simply let P hat stand in for P for a very large population. Okay, well, if there's no further questions, I'll get straight into the example. I'll read it out for you. In a huge bag of 10,000 balls, that's a big bag, a sample of 100 balls are drawn. Oh, that's terrible English, is drawn. A sample of 100 balls is drawn. Cool. 61 of them are blue. Find the 95% confidence interval, find the 99% confidence interval. So I've just tried to even be a super summary of the what you'd be asked to do. Okay, just giving you a chance to write that down, and I'll just speak to it as you go along. Is this binomial? Yes or no? For looking at the chance of drawing out a blue ball. Why, Monty? Excellent. But now I'm going to give you an extra fact. The bag is full of blue balls, red balls, and green balls. Is it binomial? Yes. Say it again, why? Yes. Right? Doesn't matter what the rest of the balls are, they can be rainbow coloured. All we're interested in is blue, and therefore not blue, as Monty said, and therefore it is binary. It's a binomial approximation of binomial. It's independent because if I pull out I might actually pause the video because this might be going on a little bit too far. I don't want the video too big. Alrighty, so how do we go about it? Might just sit down for this one. So what's p hat? Who can tell me what p hat is? M. That is the sample size. That is, well, wait, what is, someone else, before you answer that then, give me a definition of p hat. What is p hat? I said someone else. Darcy. Yes. Well, it's the proportion of the sample size with the attribute. Good. So the proportion is going to be the number that match the attribute over the size of the sample size. So with all that in mind, 61 over 100, good, which is, as a decimal, yeah, as a percentage, and as a decimal, hello, yeah, good, all of it correct. I put you on the spot there, didn't I? So 0.61 is what p hat is, okay? So now we can work out the margin of error. Now, we've got a 95% confidence. Now, this is actually a C standard question, right? The reason why it's C standard is because if I go to my info sheet, look at that. Z's been given to us. So when it's a 95% confidence interval, we can use 1.96 and be done with it. We don't have to. It's more accurate to work out Z fully, but you can use 1.96. P.S. If you remember our distributions here, 68, 95, 99.7, you know, that distribution approximation thing? They are approximations. So 95% are within standard deviations is actually just an approximate. It is actually 95% of data is 1.96 standard deviations away. But we just tend to say 2 standard deviations away because it's easier to deal with, but it's actually not exactly accurate. Okay, so back to it. So M is going to be simply, so at Z, 95% confidence, Z is equal to 1.96. And that's from the info sheet. So the margin of error is 1.96 multiplied by the square root of 0.61, p hat. And then 1 minus p hat, of course, is just whatever I need to add to get up to 1. So multiply by 0.39 all over, and the sample size was 100. Okay, thank you. You check in. Cool. Okay. All right, so there's the calculation, blah, 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 blah. And then we'll do that on our calculator, which looks a little bit like this. 1.96, I'll put my Z value in, multiplied by And I just do my full setup on my calculator. So I go Control X squared to get the square root in, and then Control divided by to get the fraction bar in. I just find that a lot easier than mucking about with division. So I've got 0.61 multiplied by 0.39, and then down on the bottom I put 100, press enter, and I got 0.095598. So that is 0.0956. And I'll pause there and ask if there are any questions before I move on. Yeah. Any questions about what I've got on the board? Yeah, this is cool. This is probably pretty reasonable then. So therefore the 95% confidence interval is just use p hat. That's kind of, we're using that as the middle. Oh man, 0. I'll leave it. 0.61 minus 0.0, oh man, 0.0956. And then it's the same thing again, but plus 0.0956. And then we're just going to simplify that. So go back to my calculator. 0.61 plus, and again, use the calculator fully just to be as accurate as possible. Plus it's faster. 0.61 plus that is equal to 0.7056, which I'm just writing down now. Oops, that was bad. I should have done the minus first. Yeah, should have done the minus first. So then I'd go 0.61 minus, that's probably faster than trying to edit this one like I do in the video, the other video. And then up to here again. Yeah, really it doesn't matter, but I just feel a lot more confident if I use as many decimal places as I can at each step and save just for writing down 0.5144. Okay, so I should have done that first and done that second just to keep my thinking straight. But there it is written down. Right, any questions? No? Amelia, you okay? Awesome. So the next one is 99% confidence interval. So this is where at the B and the A standard, they can start asking you questions where it's not one of the common confidence intervals like 95%. Even if you were given, like, I think it would be really rare, but if you were given, say, 68% confidence, then you could technically use Z equals 3, and that would work approximately. But you would, I can't even remember a question where they said do the 68% confidence interval, because that's quite low confidence, right? That's right, yeah. Occasionally 95 as well, I believe. Well, not occasionally. I'm pretty sure they always have a 95% there somewhere because that's why you're given the value. So I'll tell you now, in the test, there's one that has 95% in it. Same question, but one part has 95%. That's accessible to almost everyone because the Z value is already given to you. And there's one that's another percentage that you have to work out as well. We're not going to do a bid on it. Yeah. Okay, so let's have a look at them. But it's all the same operation anyway. I mean, I could say 2% confidence interval, and it's all done the same way. So at the 99% confidence interval, we need to work out the Z value first because we don't know it. And so that's when we draw our little diagram of a Z standard normal distribution. And we are looking for the 99%. I don't even like that. So it's probably like that, right? So there's your 99%. I really encourage you to draw the picture because the picture will help you keep your brain straight when you're figuring things out. Because what you're going to do is you're then going to say, well, if that's 99%, what am I left with on each tail? Each of the tails is, well, both tails together is going to be 1%. And so this is going to, that's going to be what? 0.5%, 0.5%. Good, Sophie. All right, we okay with that so far? Now, again, I know I said it slightly differently in the video, but I think if it were me, just so I didn't have to muck about with absolute values and stuff, I think I would just get into the habit of going, well, if I know that's a 0.5% there, I know that all of this is going to be 99.5%. Okay, so I would go straight into Z is equal to inverse norm. I mean, you could do this on your calculator first, then come back and copy it down. Just I've done it so often. It's like I can write it down before I do it. So Z is going to be the inverse normal. I know I need to be covering 99.5%, so that's 0.995. And so on my calculator, I go menu. I can go to either probability or statistics. Just to be crazy, I'll go statistics first. Then I'll go to distributions, and then I'm going to go to inverse normal. The area is 0.995. Leave everything else the same, so I can just go enter, enter, and there it is there. 2.58. That'll do. Yeah. Thank you. That's the kind of questions I want to hear. For the sake of the video, I'll just say the question was, why is it 0.995? So you mean 0.05? I'll show you what that looks like in a second. That's a good follow-up question too. How about I do that first because it all makes sense? Yes, you can. So if I do that, but I go 0.05, yes, 0.005, because that's 0.5%. 0.05 would be 5%. So if I go 0.005 and press return, I get exactly the same value except negative, like you said, Sophie. So yes, you can absolutely do that as long as you know that that you have to cut off that negative for the next step. Yep. So why? Okay, this is why. I hope this makes sense. Just stop me if it doesn't. Effectively, what we are doing is for a 99% confidence interval with, say, p hat in the middle here, then we are looking for not just from a spot downwards, we're looking for this middle area here, like I've got in red. Now, this is the standard normal, so this is Z, but if you can imagine this said p hat, then this would be the normal distribution of the blue balls, and this would represent the 99% area. Okay, so a certain distance away from p hat this way and a certain distance away from p hat that way would cover 99% of the distribution. Does that make sense so far? If it doesn't, we need to go back a little bit further, okay? So that's kind of key. You need to understand that what effectively we're doing is we're trying to see how far away from p hat in this direction and how far away from p hat in this direction we have to go in order to cover 99% of possibilities. Okay, that's what that gives us. So if that gives us 99% of all possibilities, then we're left with a tail of 1%. So these two green areas have to be 1% because we know the total area has to be 100%. So if it's 99% here, then this green and this green would have to be 1%. And then we use our symmetrical property of distributions to say, well, it's symmetrical. So if the green area is 1%, then that has to be 0.5% each. Okay, so if the question is, I still don't get the 99% bit, then see if you can put a pin on your thinking and I'll come back and talk to you individually. But if you get that we are looking for an area of 99%, the important thing to get here is that means this must be 0.5% and this must be 0.5%. And then I've got one more connection to make, but do you want to ask a question? We kind of want to say, I want an interval that covers, that gives us 99% confidence interval means I want to make the interval, in other words, from here to here, the interval wide enough so I've got a 99% confidence that the actual population proportion P would be captured in that distribution. That's basically what it means. Okay, so if I go for a 95% confidence, I'll have a narrower interval, which means that I'm less likely to get P, the unknown proportion, to be caught within that interval. So the higher the percentage, the wider the interval has to be to catch that to catch the population proportion P, which we don't know. Yeah, I mean, yes, okay, great. So that's the next connection I need to make. So when we use, oh, can I do this first question? I'll come back to you. When we use inverse norm, it asks for an area. Now, whenever it asks for an area, it always returns the Z value from that point onwards. So if we say 99%, it's not going to give us the Z value here. 99% would give me the Z value from here and goes on down that way. So what we're trying to say really is if I'm looking for the middle 99%, what would the top boundary be? The top boundary would be just 0.5% down. And that's how, so we're doing it because that's how inverse norm works. Inverse norm work says, give me the boundary value, so this value here, such that everything, not just the bit we're looking for, everything would be inclusive. So we need to say, well, where would that boundary lie? It's not going to lie at the 99% point because that's not the 99% point. That is there. Okay. To get 99% of the area there, that would only leave 0.5%. And so there, my boundary there is going to be 99.5%. So in other words, from, I'll write this and then delete it. From here to here, that would be from 0.05, 5%. I'll do it in percentages just so it's really clear. So it'll be from 0.5% to 99.5% is between those two boundaries. And if you look at the size of that, that would be 99%. So between those two boundaries, there's 99%. If I used inverse norm at 99%, I'd be saying from 90% backwards, which would be a different boundary value here. Yep. Go, M. It goes from a boundary and gives you, it assumes that you're giving it a percentage, which is from a boundary point backwards to the end. Yep. Always. Yep. No, 40. If you're doing something really dodge, if you ask for a confidence interval of 10%, then you would be saying, I would be looking for just this little narrow kind of area in here, right? That'll be the 10%. A confidence interval of 10% means I'm looking for the middle 10%. What would be left on? So what would be left on the edges? What would be the green area? Totally. It'd be 45 each. So that means that boundary point is at 0.55, 55%. Well, if it's 100% to here, and I'm going back 45%, I'm left with, not 0.55, sorry, 55% or 0.55. If this whole thing is 100% and I want the boundary here, I'm going to have to go back from 100% back 45%. So this would be 0.55. Not, that value wouldn't be 0.55. I mean, that's the area that I'll be putting in. This area here, if this area here is 45%, all of this area here would be 55%. Okay, I feel like I need to keep talking to you about that, but for everyone else, is that okay? Yeah. Yeah. On the left. Yeah, it's a good question. I don't know if that would have been picked up by the microphone. So it's kind of like if we use 0.995, doesn't it include this little bit here? And the answer is yes, it does, because we need to look at what we're trying to do. We're actually trying. We're trying to work out what that value is there that I'm highlighting now. Is that okay so far? Well, the inverse norm can only give me that value if I know the area all the way back. Okay, all the way back. Okay, so I'm kind of using the fact that I'm given 99% to work out the area that's all the way back so that I can put it into my inverse norm. Okay, so I'm given that it's 99%, which is this here. This means that I need to work out this boundary here. This boundary here is 99.5% of the way through my distribution. So that gives me my 99.5, which is all of this area. So the reason why I'm putting 0.995 in is because that's what my inverse norm function requires. My inverse norm function doesn't understand a middle area. It only understands everything from a point. So I've said I can't put in 99% because it doesn't understand that. For this boundary here is the boundary for the middle 99%, but it is also the boundary for the top 99.5%. So by working out the boundary for the top 99.5%, I'm also working out the boundary for the middle 99% because they are the same number. Does that make sense? It's the same number. So it's like I'm using a sideways calculation to work out the number that I'm looking for my main calculation. This is like by the way, if I use 0.995, then that value there will be 2.58. Oh, good. If that's 2.58 at 99.5% for the whole area, then that's 2.58 for the 99% middle. It's the same value, but we need to use 0.995 because that's the only way inverse norm will understand it. Am I making sense? Cool. All right, I get it. That's the crux, right? That's the tough thing. Okay, once that step has been assimilated, the rest of it is the same as part A, but with 2.58 instead of 1.96. So you've got 2.58 multiplied by 0.61 multiplied by 0.39 all over 100. So underneath the square root sign, it's exactly the same. So on my calculator, I will go up to that one, multiplied by, and then I just set it out again, control x squared, control divided by, that sets out my problem, 0.61 multiplied by 0.39 all over 100, and that gives me a margin of error of 0.1256. I'm just writing down, then I'll flick over. So I can see you've got all my decimal point places there, but I'm just writing down 4 decimal places because they're the most relevant. Okay, you can see, I hope, if you look at slide 3 to slide 4, that the margin of error for 99% confidence is a lot bigger than the margin of error for 95%. Again, remember that the confidence interval simply means that if I had 100 samples, I would expect, for a 95% confidence interval, for 100 samples, I'd expect the actual population parameter, which we don't know, P, to be in it 95 times. For 99% confidence interval, we're saying I would expect it to be in there 99 out of 100 times. Okay, so to get that expectation higher, I need to say, well, I'm making the interval wider. So my capacity for error, if you like, is higher the more the bigger confidence interval I want to say. Okay, so 99% confident, but it's going to be plus or minus 12.56%. Okay, so I'm 99% confident that the probability of a blue ball is 61%, of drawing out a ball is 61%, but it's with an error of plus or minus 12.56%. So what does that look like in terms of the confidence interval? We've got 0.61 minus 0.1256 and 0.61 plus 0.1256. And that is equal to 0.61, I'll do it properly this time, minus that one there, gives me 0.4844, and then I do it again, oops, 0.61 plus that old number there, and that's 0.7356. Okay, so my confidence interval is there. So what that means is that I'm 99% confident that the probability of drawing out a blue ball from 10,000 is somewhere between 48 and 79%. Pretty wide, right? But you're saying it with 99% confidence. Whereas the way to interpret this one here would be to say I'm 95% confident that it's somewhere between 51% and 71%. So it's a narrower interval, but with a lower confidence. The narrower the interval, the lower the confidence. The higher the confidence, the wider the interval. Because if remember that means that if I did 100 samples, I would expect that the population would be parameter, the actual chance of getting a blue ball, would be in there 99 out of 100 times. So in order to capture that P, that population parameter, population proportion or population parameter, I have to make the interval wider, so it catches more. This is like a little basket that I'm catching my actual population parameter in. This is a wider basket. So if I've got a bigger basket, it's more likely that I'm going to capture the value. Yep. Closer numbers in the interval. Yes. Yes. So the closer these two numbers are together, there's a difference of what, 20% between these two, roughly, and there's a difference of almost 30% between these two. So it's a wider margin, wider interval. There's one more thing I want to show, and then I'll take questions. If you get super stuck and it's in the calculator section, I mean, it's bound to be worth 4 marks or something like that, and so therefore you have to show working out. But if you get super stuck, I just want to show you it is possible. Menu, statistics, confidence intervals. Hooray. Now, the one you need to be looking for is 1 prop Z interval. So you do 1 prop Z. Number of successes, it was 61 from our trial of 100. See how it doesn't really matter whether there was 10,000 balls or 1,000,000 balls or whatever. That the population size actually doesn't matter. The confidence level, let's go for 0.99, the one we did before. Press enter. And as long as you can translate it, you're good. C lower, that's the lower end of the interval, is 0.484. C upper is 0.736. P hat is 0.61. We worked that out manually. Margin of error, ME, is 0.1256. All of these, if I flick back, 0.1256 is there. 0.4844 to 0.78356, sorry, is these two values here, 0.7356, sorry. These two. So all of these values are included in this calculation. Amelie. Listen, you got to the question, it's worth 4 marks, and you think, freaking hell, I can't remember how to do this at all. But I do remember I can do confidence intervals on my calculator. You do that, you write an answer down, and then pray to the exam gods that they might give you 2 marks instead of 1. But that's 1 or 2 marks is better than, yeah, so that's why I'm showing you. But if it was worth 4 marks and you can't show me how to do the Z value, then you haven't shown me that you're an A standard student, if that kind of makes sense. Yeah. Nope. So you could literally write the answer. I mean, you can write all of that down if you want to, but I mean, at the end of the day, we don't accept calculator answers. So if you wrote down the confidence interval as being from that to that, then you'll get a mark for writing that, right? But that's all. Okay. Sure, you could. Yep, you could do. Yeah, 100%. Good idea. Yeah. Sophie, that's a really good idea. If you've got time, it's like a 30-second calculator operation that confirms that you've got points in the bag. Yeah, I never thought of it from that perspective. Yeah, good one. Any questions, more questions about that example? Sure. Feel free to dip out at any point, guys, at this point. So the 90% interval, would be the Z diagram for it would be the middle 90%, something like that. So if the middle is 90%, what are the tails in total? Yeah, total of 10%, so it'll be 5% each. So that means that from here to here is going to be 95%. Yep. If that's 5%, then from here to the end, it's going to be 95%. And so you would go Z is equal to the inverse norm of 0.95, 0, 1. And that'll give you a value. Yeah. Okay. In general, I have a standard normal distribution. Yep. So this is just talking about standard normal distribution. That has a mean of 0, and I want to find this value here, which I'm going to call K. I'm trying to find the value K. So K would be given by using the inverse norm function. The way the inverse norm function works is that it can work out the boundary K as long as it knows what that area is there. Yes, yes. Yep. Okay. So that's how it works. So if I know what that is, if I call that, I don't know, I'm just trying to think of a thing like L%, then that would be inverse norm L%, 0, 1. Now, going back to confidence intervals, because it's the middle 90%, we need to work out what this point is here, but L% would be all of that. For the 90% confidence, so it's like this. For a 90% confidence, I need to work out the Z value. The Z value is going to be this boundary here. This boundary here is going to be made up of the 90% plus the 5% to make it 95%. Yep. Cool. Any other questions before I stop this video?